Now it's time to talk about the inverse of exponential functions, known as the logarithmic functions. Now, just as a reminder, an inverse is a reflection over the line y equals x. When you reflect a graph over the line y equals x, you basically change the ordered pairs. You flip them. So that's what we're going to talk about in terms of logarithms. Now, there's a definition of the logarithmic function. Here's the definition. The log base a of x equals y, if and only if a to the y equals x. This is the relationship between a logarithmic function, this is the log form of a function, versus the exponential form. Now, what we're going to do is we're going to flip between these two forms. Sometimes it's going to be easier for us to solve a problem if we have an equation in log form. More often than not, it is going to be easier for us to solve a problem if we put it in exponential form. And one of the things I want to point out is I pronounced this the base. Well, this is the base of the exponential function. Also, I want you to notice that in the exponential function, that is the exponent. So the logarithmic equation is always going to be equal to the exponent. Let's practice putting log form into exponential form. All right, the first one is the log base 10 of 100,000 equals 5. In exponential form, the base is 10. 5 is the exponent, so it must be equal to 100,000. And that makes sense because the way powers of 10 work is a 10 to the 5th power means a 1 with 5 zeros. B, the log base 2 of 8 equals 3. 2 is the base, 3 is the exponent, so it must be equal to 8. And it does. 2 to the 3rd equals 8. C, the log base 2 of 1/8 is equal to negative 3. The base is 2, the exponent is negative 3, and that must be equal to 1/8. Well, remember when you have a negative exponent, it says flip the fraction, so 2 to the negative 3rd is the same as 1 over 2 to the 3rd, which is 1 over 8. D, log base 5 of s equals r. Well, the base is 5, the exponent is r, and that will equal s. Now let's evaluate the log base 10 of 0.0001. Now this time I didn't tell you what it's equal to, but this is what I do want you to notice. First of all, 0.0001, that's 1 over 10,000. Because this is the 10th place, the 100th, the 1000th, the 10,000ths. If I set this equal to x, and then rewrite it in exponential form, I'm going to get 10 to the x equals 1 over 10,000. Well, the only way to raise a number to a power and get a fraction is if the exponent is negative. So the question is, negative what? Well, the nice thing about powers of 10 is you just need to know how many zeros there are, and there are 4 of them. So the answer is negative 4. Let's talk about powers of 10 here for a minute. 10 to the 1st is 10. That's because it's a 1 with 1 0. 10 to the 2nd is a 1 with 2 zeros. 10 to the 3rd is a 1 with 3 zeros. 10 to the 4th is a 1 with 4 zeros. That's really the cool thing about powers of 10. Now let's talk about what happens when you have negative exponents. So 10 to the negative 1st is 1 over 10. It's 1 over a 1 with a 0. 10 to the negative 2nd is a 1 over 1 with 2 zeros. 10 to the negative 3rd is 1 over a 1 with 3 zeros. 10 to the negative fourth is a 1 over 1 with 4 zeros. Pretty cool, huh? Now let's talk about some properties of logarithms. The first property is that the log base a of 1 is equal to 0. The reason that's true is because if you rewrite it in exponential form, you get a to the 0 equals 1. Anything to the 0 power is 1. The second property is the log base a of a equals 1. That's because if you rewrite it in exponential form, you get a to the first power equals a. The next property is the log base a of a to the x is going to equal x. Because when we write this in exponential form, you get the base of a raised to the other side as x is equal to a to the x, and those two sides equal each other. The last property is a little trickier. It says a raised to the log base a of x is equal to x. This one's written in exponential form rather than logarithmic form. So basically it says if I go the other direction, if I rewrite this in log form, the log base a of the other side is x is going to equal the exponent, and the exponent is log base a of x. Let's look at some of these properties. I want to evaluate the log base 5 of 1. Well, the first thing that I want you to do is I want you to set equal to x. And then I want you to rewrite it in exponential form. Well, the only way to raise 5 to a power and get 1 is if x is 0. Let's set the next one equal to x. I want to evaluate the log base 5 of 5. Well, if you rewrite in exponential form, you get 5 to the x equals 5. Well, x must be 1. In C, the log base 5 of 5 to the 8th equals x. So now we're going to rewrite this as 5 to the x is equal to 5 to the 8th. So x must equal 8. Now let's look at the last one, D. 5 raised to the log base 5 of 12. This one is already in exponential form. So in order to figure out what x is, we're going to rewrite it in logarithmic form. So it's going to be the log base 5 of x equals the exponent, which is log base 5 of 12. X must be 12. Earlier I had said that the logarithmic function was the inverse of the exponential function. Well, if this is the exponential function, the inverse of it, the logarithmic function, is a reflection over the line y equals x. So it's going to look something like this. I want you to notice that the logarithmic function, here, let's call this y equals a to the x. So this is log, y equals the log base a of x. Anyway, I want you to notice that the log function, instead of having an asymptote of the x-axis, its asymptote is the y-axis. It passes through the point 1, 0, unlike the point 0, 1 for exponential functions. Its domain is x is greater than 0, and its range is all real numbers. There is a special type of logarithm called the common logarithm. The common logarithm is the log whose base is 10. This is the button on your calculator. The log button on your calculator is base 10. Any other base, we need another way of solving the problem. Let's evaluate some logs using our calculator real fast. So the log of 0.01, the calculator spits out -2. The log of 0.1, the calculator spits out -1. Remember, these are exponents. They're powers of 10 that give you the number that you're taking the log of. The log of 0.5 is -0.301. The log of 1 is 0, because really that's 10 to the 0 equals 1. I'm going to jump over to the log of 4, which is 0.602. The log of 5 is 0.699. And the log of 10 is going to be 1. The perception of the loudness B in decibels of a sound with physical intensity I in watts per meter squared is given by B equals 10 log of I divided by I sub 0, where I sub 0 is the physical intensity of a barely audible sound. Find the decibel level, the loudness, of a sound whose physical intensity I is 100 times that of I sub 0. Well, I don't actually know what I or I sub 0 is. I do know that they wanted me to say that I is 100 times I sub 0. What I'm going to do is I'm going to take this quantity and I'm going to substitute it into this equation. So B is equal to 10 times the log of 100 I sub 0 over I sub 0. Well, guess what's going to happen to those I sub 0s? They go away, and you're left with 10 times the log of 100. That is something that I can shove in my calculator. Well, I find out the answer is 20 decibels. There is a last type of logarithm called the natural logarithm. The natural logarithm is the log whose base is e. Well, this is also a button on your calculator. It's abbreviated ln. So the natural log of x is the same as the log base e of x. Now, the properties of the natural logarithm work exactly like the properties of regular logarithms. So if you have the natural log of x equals y, then in exponential form, it's going to be e to the y equals x. Because remember, the base of the natural log is e, even though we don't see it. The properties work the same. So the natural log of 1 is equal to 0. Why? Because e to the 0 is 1. The natural log of e is 1. Oops, I should have written that better. There we go. Why? Because e to the first is e. Let me phrase this another way. Natural log and e, they're inverses of each other. You remember what inverses do to each other? They cancel. 3. The natural log of e to the x is x, because you get the base of e raised to the other side as x is equal to e to the x. And the last one, e to the natural log of x, is also going to equal x. Now that one's in exponential form, so if you rewrite it in log form, you get the natural log of x is equal to the natural log of x. Let's do some evaluating with the natural log. I want to evaluate the natural log of e to the 8th, so we're going to set this equal to x. First, let's rewrite it in exponential form. So e, because remember ln is the log base e, raised to the other side, which is x, equals e to the 8th. Well, x must be 8. In b, the natural log of 1 over e squared. Let me rewrite that first. I'm going to rewrite that as the natural log of e to the negative second, because that's going to make this problem a little bit easier. So now I'm going to rewrite this in exponential form. E to the x is equal to e to the negative second, so x must be negative 2. The last one, natural log of 5, that you can just plug into your calculator. You plug it in and you get 1.609. The last problem we're going to talk about is the domain of f of x is equal to the natural log of 4 minus x squared. So I'm going to do this in a couple ways. The first way I'm going to show you is algebraically. We cannot take the natural log or any log of a negative or of 0. So what we're taking the natural log of has to be greater than 0, not greater than or equal to. If you go about solving this for x, you end up with the absolute value of x is less than 2. Because remember, we can't have negatives, so x can't be negative 2. Well, the absolute value of x is less than 2. There is a little formula for solving an absolute value inequality. It's that x has to be less than 2 and x has to be greater than negative 2. So it's really just this inequality. Now let's talk about it graphically. Graph in your calculator the natural log of 4 minus x squared. What you end up seeing is this little half circle that kind of looks like this. Well, because you can't take the natural log of 0, that means that x cannot be negative 2 and x cannot be positive 2. But apparently it can be every number between them. So that's another way of determining the inequality. Remember, we can also write this in interval notation. Oops, got to write it correctly in interval notation. It would be parentheses negative 2 comma 2 parentheses. Either answer is acceptable with me.